My name is Joyce Lee, Technical Marketing Engineer with Xilinx. Today, I will talk about the design methodology of building accelerated applications on a Xilinx FPGA. Here is the agenda for today. Firstly, I will introduce the design methodology concepts, and then I will talk about how to architecture an application. After that, we will look into some details on how to develop efficient kernels. And lastly, I will show you a real example by leveraging the methodology. Let me start with this word, acceleration. Obviously, it's all about making your application run faster than a purely software-based application. That's what we are showing here at the top of the slide. We have a bunch of tasks running at CPU that mostly will be sequential-based, one task executing after the other. In some cases, this may be good enough performance, but in many cases, will be too slow. And we will be looking into accelerating things. At the bottom of the slide, it shows running some of the tasks in hardware concurrently. For example, task 2 is running in parallel with tasks 3 and 4. This is an abstract explanation of what you can achieve with FPGA acceleration. It's all about leveraging parallelism to increase performance. Why FPGA is so effective comparing to CPU or GPUs? The answer will be CPUs or GPUs all come with fixed architecture. But when it comes to FPGA, the architecture is actually programmable. In other words, you can create architectures optimized for the needs of your application. FPGA gives you tremendous flexibility so that you can customize your architecture. Also, another very important factor is the memory hierarchy. Unlike CPU or GPU, you can craft the memory architecture that customizes to your needs at FPGA, which means you can get the data that you need with the bandwidth that you need and fit to your processing units in an optimal fashion. For task parallelism, you are probably doing it as CPUs in threads and GPUs in SIMD, whereas in FPGA you can pretty much step in any kind of parallelism, and I'll show you more in next slide. The key takeaway here is FPGA offers tremendous possibility to achieve or optimize on your needs. As a developer, you will have to think about all of these ways to implement parallelism. Find the ones that most appropriate to your design. There are lots of things you can think about: data level, task level, instruction level, and bit level. Data level parallelism means to process multiple data at the same time. Task level parallelism is in higher level, that is shown in the picture to the right. Unrelated tasks can be executed in parallel to save overall latency. Instruction level parallelism is that multiple instructions can be executed in parallel or in pipeline mode. Also, you may customize the processing data width, which is bit-level parallelism. For example, a 512-bit data means more parallelism comparing to a 32-bit data. As you understand by now, FPGA acceleration is different from traditional software development. There are lots of similarities, for example, starting from same languages, C or C++. But beyond that, there are lots of differences. That is the reason why having a methodology is very important. Methodology is going to help you approach the problem, analyze, and make the right decision to obtain the optimized results more rationally. This is also what this presentation is about. If you would like to know more details about methodology, this is also included in the VITIS online documentation. There is a chapter named Methodology for Accelerating Applications with the VITIS software platform. And there are also a bunch of examples on Xilinx GitHub repository. Here we will talk about methodology in two parts: architecting the application and developing efficient kernels. Before we go to details, I need to show you two more slides. Starting with this, as a reminder, even the tools are great, even if the methodology are very efficient. The key to success is really you taking charge and analyzing your design. Nothing replaces that. The developer makes key decisions about the application architecture by determining which software functions should be mapped to FPGA kernels, how much parallelism is needed, and how it should be delivered. Then the developer implements the kernels. This primarily involves structuring source code and applying the desired compiler pragmas to create the desired kernel architecture and meet the performance target. Here, I will now read the content inside each box, since they will be restated in the following slide. This table can also be found in VITIS documentation that I mentioned just now. Tools are great, but not magical. For example, tools will now generate double sort from quicksort. It's you who have the responsibility to not only think about the functions you are about to achieve, but also the algorithm that you will use to implement that functionality. Have clear performance goals. Understand the data dependencies within and across the compute stages. Understand which tasks can run in parallel and which must be in sequential. Determine where and how you will achieve parallelism. Determine how data should flow for optimal performance. By applying this methodology, you will get more predictable results. The other thing I want to mention before diving deeper into the methodology is that you don't have to do everything by yourself. Xilinx has invested significantly in creating libraries you can use in your project so that you don't have to redevelop those functions. Check out documentation and libraries to see if anything you can leverage and reuse them. Let's start from architecting the application. It's really about making key decisions about application architecture. Determine which software functions should be mapped to FPGA kernels. Determine how much parallelism is needed and how it should be delivered. Having a goal is very important. The goal is what you keep measuring in every step of the development process. You will determine how much parallelism is needed, and you will also determine how you want to implement that parallelism, whether it's within compute units or across different compute units. You will also be making decisions of architect the software to minimize CPU idle time and keep FPGA accelerators utilized, optimize data transfers to and from the FPGA, not only about building super efficient kernels, but also you want your entire application to work as efficient as possible. Usually, the first step is to start measuring the constraints. You will be targeting a FPGA or FPGA accelerator card. Those cards are not infinitely capable. You are going to have constraints or bounds. You will need to know what's the PCIe bandwidth, the maximum clock frequency, the global memory capacity, global memory bandwidth, how many ports can be connected to global memory. It's very important to start by assessing all of these constraints. We have provided documentation and examples to help you learn about those. And it's very important to understand the performance ceiling of your application. With that in mind, the next step is to figure out what are good candidates for hardware acceleration. This formula of computational intensity is very simple, but works very well. It starts with measuring numbers of operations over the number of memory accesses. And why that is important? Really, when it comes with FPGAs, you can parallelize easily. The fabric allows you that. But memory accesses or I/O accesses are expensive, especially when you are accessing off-chip memory, for example, DDRs. Those transfers might hurt the performance. So really, what you want to do is targeting operations or functions which have high numbers of operations and low numbers of memory accesses. And if you can find those functions, it will typically be better candidates than others. Higher the computational intensity, the lower of the overhead of moving data for processing. The next question is, how much parallelism do you need to achieve your goal? Here is another formula. It's just an estimate, as lots of factors can impact the performance. But it will give you a pretty good feel for how much parallelism is necessary to meet your performance goal. And it's pretty predictable. Once you have understood and computed parallelism that you need by using the formula, the next question is how to do that. And here you've got a number of options. You can execute operations in parallel within a kernel, or you can execute multiple kernels in parallel within the system. There are many different ways available, and you have to determine which combination of approaches is the best suit to your application and your goals. At this point, we've talked about hardware side. There are also lots of things you can do in software side too. As shown here in this slide, you can also architect the software application for parallelism, such as filling in the CPU idle time by making FPGA kernels running. Keep the FPGA kernels up and running for as long as possible. And also, traditional software techniques like thread will also help you achieve the goals. Vitis provides a powerful capability to visualize your design results. One good example is The timeline trees report. Timeline is very nature presentation to show how the system behaves. You can see not only the accelerator and software, but also how they execute relative to each other over time. And you can form that mental picture, or even better, draw it. You will start shaping a spec and profile your design. If you can visualize it, you will pretty much have the blueprint to build your application. Another reason why it's very important is that the tool will generate those kind of views for you as you run the application in emulation or at real system. So you will have what you expected and what is the result to compare. Normally, they will not match right away, but you will see what's different from measured results and figure out how to change things to improve to the best results. Conceptualize the desired application timeline that will definitely increase your chance of achieving the performance goal that you are looking for. In the following slides, we will talk about some details on how to develop efficient FPGA kernels. By now, you should have pretty good understanding against architecting, and you really want to implement these things. So, in this section, we will talk about implementing kernels using C or C++ as input languages, and using HLS as compiler to build kernels. So, when it comes with developing C or C++ kernels, there are 5 steps, as you can see from the screen. There are steps for microarchitecture and microarchitecture. The ways of doing that could be slightly different, but it should all start with clear performance goals. You should understand the data dependencies within and across the compute stages. Understand which tasks can run in parallel and which must be in sequential. Determine where and how you will achieve parallelism and how data should flow for optimal performance. To do microarchitecture optimization, I want to talk about the principles of HLS code development. There are some key concepts, especially when it comes with building accelerators. The first one is I/O accesses or memory accesses are expensive, especially when you go off-chip to DDR. So, a good recommendation is to encapsulate all of these I/O accesses in dedicated functions. It's not mandatory, but it's very helpful for optimization purposes. It will not only help to get good results, but also help structuring the kernel and the process. Something else to know when it comes with HLS is task-level parallelism. We cannot do it from a so-called arbitrary C code. If you want to achieve parallelism, put them into functions. Functions will run sequential in your C code, but HLS can parallelize that. On the contrary, we have sequential loops. Most of the time, we will get it run sequentially in hardware. Lastly, when it comes with instruction parallelism, as you can see, it mostly achieved through pragmas. Sometimes you may need to do some code restructuring. Those principles are important, and hopefully this will cover what I'm going to explain in the next few slides. Let's first talk about microarchitecture of the kernel. It's all about first of partitioning the code to get the design architecture. So divide your code to load, compute, and store. As the name suggested, load and store are all about bringing data into and restore out of the kernel. Write tightly nested loops to infer bursting transactions to global memory. Bring data into the accelerators either through FIFOs or local cache, which can be DRAM or URAM. But again, think about data movement, how to efficiently move data from outside of the kernel into local data structures. Compute is obviously where you do the processing. It can be a single function, but most likely you will have multiple functions because most of the times you want to decompose the compute to sub-functions. Make sure you measure or estimate the throughput of each block. The system won't be running faster than the slowest blocks. So throughput of each block should be greater than your goal. And lowest level block should only contain a single loop nest or loops that need to run sequentially. We'll talk more in next slide. For microarchitecture, this is where we have loops, and we'll try to optimize loops to meet performance targets. So loops, how do we measure performance? There are three important parameters that influence the performance of a loop. Trip count is the number of iterations of the loop. Steps is the duration of single loop iteration. II, or initiation interval, is the number of clock cycles between the start of two consecutive loop iterations. As shown in this figure, the loop latency is a function of them all. So reducing any of the three factors will improve the total latency. Here, we suppose the clock frequency is fixed. As a result of a compiler, tools give you lots of reports, including loop profile, showing you all the numbers I talk about. Whiteys provides a graphic tool to view the reports and identify the bottlenecks. After locating the bottleneck and combining that with your understanding of the algorithm, you may adopt different methods to optimize the design. For example, loop and row pragma can be used to reduce trip count as it increases the level of parallelism. Array partitioning or local buffering will benefit II as it eliminates the data access contention. Loop carry dependency is a common factor to cause suboptimal II results. Eliminating the dependency will help to get better II value. So use the reports and use the information given by the tools, compared with your expectations, and make the decision towards your goals. We have a built-in tool called Whiteys Analyzer, which is a GUI tool that provides a single entry to view different reports, such as guidance, profile summary, and timeline trees. It doesn't matter if you run the design in GUI flow or command line flow. Whiteys Analyzer can be used to view the reports in a convenient way. Guidance report contains a list of errors, warnings, and suggestions related to the run or the build process. You can review the guidance messages to make any changes that might be needed in your code or build process. Emulation is playing a critical role in the design verification process. It can test the hardware and the software integration and evaluate performance results. The profile summary provides annotated details regarding the overall application performance. It is created under both emulation and hardware runs. From it, you may investigate the kernel execution time and data transfer statistics, etc. The screenshot in bottom right is showing a timeline trace report. The application timeline collects and displays host and kernel events on a common timeline to help you understand and visualize the overall health and performance of your systems. The graphical representation lets you see issues regarding kernel synchronization and efficient concurrent execution. Now, you should have already got many useful information about design methodology. Let's take a look at an example design on how to apply those methodologies to optimize your design step by step. The example we chose here is a very common algorithm in machine learning. The K-means clustering algorithm. K-means clustering is a method of vector quantization that is popular for cluster analysis in data mining. K-means clustering aims to partition n observations into K clusters, in which each observation belongs to the cluster with the nearest mean, serving as the prototype of the cluster. Here, we will use an open source code and accelerate it on FPGA. We will adopt the methodology that was discussed just now to optimize the design, and the performance is compared with CPU results for benchmarking purpose. In this stage, we will create an initial version of the design. The CPU code will be ported into an FPGA kernel and host module. The kernel code is going to be compiled by HLS, so we need to make sure the code is compliant with all the HLS coding style. After migrating the design, we will use HLS to estimate the performance. Here you can see the estimation result listed in the table. The result is much worse than the CPU result because all the operations are carried out in a sequential way. We recommend using HLS for initial performance estimation as it doesn't require to run emulation or execute on real board so that it can save design building and testing time. In this stage, our aim is to improve efficiency of data access. By default, the kernel will access to external memory such as DDR to read or write the data. And the DDR operations is always along with long latency. Therefore, we can create a local buffer inside FPGA using DRAM or URAM to avoid redundant access to DDR. As we can observe from the code, for every point, the data in clusters is read again and again. And so we decided to transfer this data stored in clusters and features to a local buffer. In this way, the II of the loop can be significantly improved. Also, we can use burst read and write capabilities for DDR access by adopting correct HLS coding styles. The intent of using burst operations is to increase the throughput. After making those two changes, you will see that FPGA time is reduced a lot, but still worse than the CPU data. We still got a long way to go. In this stage, we will take a look at data type optimizations. As you may know, floating point arithmetic operations bring with higher cost in FPGA implementation on both latency and resource. To enhance on that, we can replace the floating point data with fixed point data type. The modification is quite simple, as shown in the code snippet here. You just need to change the defined value. But the impact is huge. As you can see in this table, the FPGA performance is already similar with the CPU result now. So this gives us a hint that always considering to use efficient data type as long as it can satisfy the quality requirement. From this stage on, we will touch the essence of FPGA's powerful advantage, parallel processing. We will start with parallel data processing, which means processing multiple data at the same time. To realize it, we will use HLS and row pragma on loop implementation. And we can define how many points we are going to process at the same time. The trade-off is between resource utilization and performance boost. Here from the table, we can see that by processing 16 points in parallel, the execution time is greatly reduced to 4.9 minutes. Also, it is very easy to try with different numbers of parallel processing points in HLS. The iteration time is also very fast. In this stage, our aim is to restructure the data channel to transfer more data between kernel and DDR. The DDR data channel is in 512 bits wide, so we will pack 15 points into same data to maximize the transaction bandwidth. Please remind that house code also needs to be restructured to provide 15 data in parallel. With these changes, the FPGA execution time is down to 33 seconds. From this stage on, we will measure the performance by running the design on actual hardware. This will be more accurate comparing to the HLS estimation numbers. In the last step, we will adopt a higher level parallelism to further enhance the overall latency. We are going to instantiate multiple kernels, or called CUs, in the design, and each CU processes different subset of data. To achieve that, both house code and kernel code need to be restructured. The number of CUs is determined by yourself depending on the algorithm and the resource utilization. By adopting this method, the execution time is reduced to 16 seconds now, which is 255 times of performance boost comparing to the CPU result. The past several slides are used to introduce a step-by-step optimization methodology, which is quite close to a real design phase. We encourage you to adopt it in your applications when possible, and if you want to find more information, please refer to the online collaterals targeting HLS and VITIS.